Hello, everyone. So in this first video, I want to discuss some good graphing techniques, like things that you will need to do to create good graphs. And actually, in this course, we'll be using something called Pascal Capstone to create all of our graphs. It'll be done on your computer. Then I want to talk about something called accuracy and precision, like define those terms. And compare them, and then compute measures of both accuracy and precision. So that's sort of the goal of this first video. So let's begin by examining this graph. So this is really an example of a poorly drawn graph. Why? What are some issues with it? Well, first thing, if you notice here that there really are not good labels, like you have A and F, that's something, but you want more explicit labels, like maybe this is acceleration on the y-axis, maybe this is force on the x-axis. Okay, so you want to make sure you have good labels. Along with labels, you need units. So what is the acceleration measured in? Is it measured in meters per second squared? Is it centimeters per second squared? You want to make sure you have units. Same thing with force. Is it measured in newtons? Is it measured in dynes? And then with the labels and units, you always want to make sure you have a title, right? Some title that describes the graph itself. So usually a good title name to use is you can simply call it the y variable, which is often called the dependent variable. So let's say it's acceleration in this case, versus the x variable, which is the independent variable. So you could title this graph acceleration versus force, and that would be fine. Okay, then there's a couple of subtle things as well here. So if we wanted to describe the relationship between this variable, let's say acceleration and in force, this may not be the best way to describe that relationship. So here I have my data points, right, plotted in blue, and I just have line segments connecting each individual data point. But if I want to show like an overall relationship between those two variables, this may not be the best way of doing it, right? A better way may be to fit some type of function, right? Some type of curve through your data points. In this case, it's probably a line. So we'd want some sort of like line of best fit, something that minimizes the errors, right? So some line of best fit through all of our data points. Okay, and then the last point is really subtle, but each of these data points have some error associated with them. They probably were derived from taking multiple measurements. So usually this error is represented by using error bars, maybe signifying like plus or minus one standard deviation. That's one way of doing it. You could circle the data points just to show like qualitatively there's some error associated with each data point. But typically you represent the fact that there's some error, right, with the measurement of each particular data point. Now for this course, you don't have to worry about that too much. You're going to be creating again your graphs on the computer using Pascal Capstone. You don't need to indicate the error, but if you were to do it by hand, you should have like some indication of the error. Okay, so let's look at the second page here. On the second page, this is an example of a graph that's drawn well and it has all the features that we want, right? So in this case, there's nice labels here, right? Range is on the y-axis and angle is on the x. We have units. The range is measured in centimeters. The angle is measured in degrees. This, by the way, is a data taken from launching a projectile, like shooting a marble at different angles. And the data is plotted here in blue again. And in this case, my best fit happens to be a sine function. So there's like a curve of best fit. This red curve here is like the best fit, least squares fit through all the data points. And again, don't worry about this too much, but what I also did was I circled each data point to show that qualitatively there's some error associated with each of those data points. Okay. And I have a title. By the way, you could have just titled this range versus angle, and that would have been fine for the title. Okay. Oh, next page. This is just a reminder on how you would calculate slope if you were to calculate it by hand. Now, again, for this course, When you do these graphs on the computer and you do a line of best fit, it'll give you the slope information. So you don't have to necessarily calculate it by hand. It'll give you that information. It'll give you the slope. But if you were to do a graph, let's say by hand, let's say we have these data points in blue here plotted, and I'm actually plotting the velocity of some object in meters per second versus the time in seconds. And it happens to pretty much be linear. Okay. So I do a line of best fit, sort of trying to minimize the errors here, like a least squares fit. And then let's say I want to calculate the slope of that line, which it turns out it's going to be the acceleration of the object, right? The slope of that line. Okay, here's the key point here. The thing that you don't want to do is you don't want to just use two of your original data points and calculate the slope between those 2 points. You actually want to calculate the slope of the line from the line of best fit. So you would pick 2 points on the line of best fit. Let's, in this case, I picked a point here where the time corresponds to 5 seconds, right? So that's down here. And the velocity corresponds to 14 meters per second. Then I picked a point here where the time corresponds to 15 seconds. And then the velocity corresponds to 34, I guess right here, 34 meters per second. So remember to calculate the slope, it's always going to be the rise over the run, right? Or in this case, it's the change in the variable that's on the y-axis. So change in velocity. You could even think of this as like V2 minus V1. So 34 minus 14, that's where the 20 comes from here, divided by the change in the variable on the x-axis, which in this case is time. So it'd be 15 minus 5. Or you could write it as t2 minus t1. And that's where the delta t equals 10 comes from. And then if I take the ratio of those two numbers, right? So it's rise divided by run. So 20 divided by 10, I'm going to get 2. And it has units of meters per second divided by seconds, or meters per second squared. So again, it turns out in this case, that slope is the acceleration. It'll be 2 meters per second squared. But the key point here was you calculate the slope of the line of best fit. So you use 2 points on the line of best fit, not two of your original data points.